Now that you've been introduced to the idea of a definite integral, let's explore why it is that we will be able to evaluate a definite integral by using the anti-differentiation process. So back when we were talking about antiderivatives, remember we had something like this, and we would read this as the antiderivative of 2x plus 1 dx. And what that meant at the time was to find the original function whose derivative is 2x plus 1. And you learned how to do that by using the power rule for antiderivatives, and I'm sure you could very easily figure that out really quickly. So now we're just going to look at a slightly different interpretation. And instead of the interpretation of finding the original function, whose derivative would be 2x plus 1, now we're going to think of it as really finding the area under the curve f of x equals 2x plus 1. If you go ahead and calculate in your head what the antiderivative of 2x plus 1 is, you hopefully got x squared plus x plus c. And you might remember we referred to that as a general solution. It represents a general equation, though, now for the area under the curve. Let's connect this back to something we've done before with derivatives. All right, suppose you had the function y equals x cubed plus 2x squared. Remember back when you learned how to find derivatives, of course the derivative of that function would be 3x squared plus 4x. And we refer to that as a general equation for being able to find the slope of the tangent line to that original curve at any point x. And all we would do is substitute any x value into that derivative expression in order to get the exact slope at that x value. So for instance, if we wanted the derivative, the slope of the tangent line at x equals 1, we would substitute in 1. If we wanted the slope of the tangent line at 2, we would substitute in 2. Well, this is now something similar. That x squared plus x plus c, not only does it represent the original function, whose derivative is 2x plus 1, but with a slightly different interpretation, it now represents a general equation for finding the area under a curve. But that kind of leads to another question, is that we need boundaries between which we're going to find that area under the curve 2x plus 1. So suppose we were to consider finding the area in between x equals 1 and x equals 2. If you take a look at it, maybe look at it sideways, tilt your head either left or right, it basically looks like a trapezoid. So one thing we could do is use our geometry rules in the area to get the area of a trapezoid to find the area of that shaded region. Well, hopefully you remember that area of a trapezoid you can get by 1/2 the height and then times the sum of the bases. So if we were to apply that to this, now again this is where you have to look at it sideways. We can think of this length over here on the left as B1, and maybe this one over here, we can refer to that as B2. And this in here is really your height. So if we were to go ahead and do that then, to get the area of that trapezoid, we would have 1/2. The height is 1 because it's going from 1 to 2. And that one base is 3 high, the other one is 5 high. So the area then would be 4. So easy to use geometry to find that. And you're going to find as we move forward that a lot of times you can use geometry rules to find area under the curve. This is a great example of that. Here we use trapezoids. Sometimes you'll be using semicircles or just rectangles or squares. Now let's transition though to why it is finally we can do this with antiderivatives. So you were introduced earlier to a definite integral. If we were to express the fact that we want to find the area under this curve 2x plus 1 in between x equals 1 and x equals 2, it would look like this. We would read this as the integral from 1 to 2 of 2x plus 1 dx. Now let's talk about some of the vocabulary and parts of this. The 1 is the lower bound of integration. You were introduced to that phrase earlier. The 2 is the upper bound of integration, and you always read it bottom to top, so this would be the integral from 1 to 2. 2x plus 1 is the integrand. You were introduced to that term when we did antiderivatives. There's your dx that's required, your differential. Now remember when you did the antiderivative earlier, the antiderivative of 2x plus 1 was x squared plus x. Now remember there used to be a plus c here. Right? We don't need that anymore because we know the two x values between which we want to find the area under the curve. So notice how there's no plus c here. So the x squared plus x, that's your antiderivative. We're going to evaluate this eventually from 1 to 2. And the way in which you see this written, this is typically how we write it. The way in which we evaluate this, we substitute the 2 in first. So if you do 2 squared plus 2, that's where the 6 came from. Minus, it's always a minus. Now we substitute in the lower bound, and we substitute in the 1. So if we do 1 squared plus 1, that's where the 2 came from. And voila, notice you get the same answer that we got by using the trapezoid area formula. So this is why it is, and we could go on and show you lots of different examples of doing maybe an area under a curve with geometry rules first, and then evaluating them this way with antiderivatives, and you always get the same answer. So as we mentioned before, this is what we refer to as a definite integral. And anytime you have a definite integral like you see here, it's implied that the interpretation is that of finding the area under a curve. This is opposed to what you did earlier with indefinite integrals, also known as antiderivatives. Those were the ones with the plus c. That interpretation is working backwards as we did to find the equation of the original function when you know what the derivative should be. So depending upon really how this looks and is presented to you, there's really two different interpretations of what's implied. A definite integral, the implication is you're really trying to find area under a curve. Indefinite integrals and antiderivatives, you're finding the original function working from the derivative. So welcome, ladies and gentlemen, now officially to integral calculus. So yes, you have calculator programs that will do this for you. So let's take a look at those. One is built in. Actually, both are built in. So let me walk you through those, and we'll use this 2x plus 1 as the example. So we'll go in the order that you see them here. The first one is going to be found under Math 9. You might remember Math 8 is where we did a numerical derivative. Well, this is Math 9. Notice the notation. It's function integral. That's what that stands for. Those of you who might have the older operating system, this is the order in which you'll have to type everything in the parentheses. You'll have your function under y1, so you'll simply pull up y1, comma, this is always an x there in that second spot. Always, 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 at least for our purposes right now. Then you have the lower bound value, the lower limit of integration, and the upper limit of integration in that order. So let's take a look at that, and I can walk you through one. Let's go under y equals. Let's put in that 2x plus 1. And if you go back to your quit screen, bring up Math 9. You can either scroll down, arrow down, you'll see it says function integral, or just hit the 9 key. Those of you with the newer operating systems, you will look like this. Again, those of you with the older operating system, yours here will say that function integral, and you'll be prompted with the first parenthesis. So remember, this we were trying to find the area under the curve from 1 to 2. You can just use your up and down arrows and side arrows to move over. Your integrand, you can just either type in 2x plus 1, or since we have it under y equals, you could bring up y1. And then there's your differential. And when you hit enter, voila, there's the 4. So let me show you the other one that's built in. Let's go ahead and graph that 2x plus 1. Just do zoom 6 if you would. The other one, this is another one of those functions that you've been seeing a lot of but never knew what it did. If you do second trace, you now know all of these because look at what that last one is. If you either arrow down to that last one or just hit 7, it's going to prompt you first for the lower limit. So that was 1 in our case, so just hit 1 and enter. Notice how it actually draws the vertical line. On everybody else's, you probably see this nice little triangle marking the lower limit of integration. Now you'll notice it's prompting you for the upper limit, so that was just 2. So hit 2, then enter. Notice how it shades the area. Geez, it looks just like the one we had. And notice down here at the bottom, It gives you here the interval, at least on mine it does, and there's the answer of 4. So those are two functions. This one, a lot of people like if you like the visualization of it shading in the area for you. You don't necessarily have to. A lot of people, and probably the one you all will use the most often is this Math 9. Once you get really good at antiderivatives and integration, you'll notice we get to the point later on this year where pretty much you don't even have to show your work. You can just do everything in the calculator. For now, though, you're still showing your antiderivatives because we need to make sure you know how to do these by hand. So that still leaves the question, you might remember our little historical overview of where all this came from. Well, we would be very remiss to talk about this and not talk about the controversy that arose over the development and quote-unquote discovery of the calculus without mention of Sir Isaac Newton and Gottfried von Leibniz. Take a look at their dates during which they lived, very much contemporaries. Isaac Newton, of course, being from Great Britain, Gottfried von Leibniz from Germany. So let's hear a little bit more about them.